Hello, how are you? Today I'd like to continue talking about the Bayes probability, and in particular about something called the Bayesian networks. This is a topic from machine learning, and I've checked, it still seems to be very relevant. Uh, on the screen, I have an example from a place on the web. Many of these examples on the web appear many times. Usually they come from a textbook or from some article, and they keep getting repeated over and over. So here's our problem. We know that the world is suffering from something, but it's a disease that only strikes 1 in 1,000. Now, we have a test to see if a person has it. But our test is only 99% accurate. If you take the test and you prove positive, what is your chance that you have the disease? And if it's not very good, then would a second test help? That's the question. Now, we know a lot of things. We know a lot of conditional probabilities here. And remember that with Bayes, we can flip conditional probabilities around, and that helps a lot. So what we are trying to discover is the probability that you're infected, given that you have a positive test. That's here. According to Bayes, that means is the probability that you get a positive test if you're infected times the probability you're infected divided by the probability that you get a positive test, positive results. Well, we have the probability that if you're infected, you get a positive result because we know how accurate the test is. We have the probability of infected. The only thing we don't have is the probability that you get a plus test. So you have to be careful of how to figure this out. How could you get a plus test? Well, either you have it, an infection, or you don't have the infection. Now, the probability that you're going to get a plus test equals the probability you're going to get a plus test if you have it, plus the probability that you're going to get a plus test if you don't. But then we have to multiply by the percentages. What that is, here I've written it down. If you look at the group that's not infected, the chances are 0.01 that they're going to get a positive result. If you look at the ones that are infected, it's going to be 0.99. Now, if you want to know how often you're going to get a positive test, you have to look at the number of times, the percentage that are not infected times the number of positive tests, plus the percentage that are infected times the positive if infected. Where you can think of this as Venn diagrams. We're splitting up the world into non-infected, infected, and we have this plus that goes across the two of them, and we need to get the information on what's the probability of the plus. Well, that's easy to compute. We have all the information. I got 0.01098. I got that from going to Excel, since I don't trust my arithmetic. Now, that means the probability that you're infected if you get a plus is only 9%. I know that surprised me when I looked at this example. It seems very low, and but the mathematics works. Now, the question is, what if you take a second test? But remember, when you're taking the second test, you already know what the probability is that you're infected because you have that from the first test. So the second test is going to look the same. It's the probability that you're infected, a given test 2, positive, equals the possibility that your test 2 is positive if you're infected, divided by the probability of test 2 positive. The test 2 positive, this is where the change is. The probability that you're infected has changed because you took the first test. And the probability that you're not infected has changed. You use that information in your new one. And surprisingly, when you do all the arithmetic, by the way, I left something out. I just realized the P infinity. I thought something was wrong. P infected has to go there. I have it right down here. I had it wrong up there. Look at that. With 2 tests, it's a 91% chance, which is quite a difference. Now that's how these work. Turns out that this example comes from this website. You can look at the website if you want. I have another example from a different website. And again, this is one that pops up all over the place. The website I'm using here is from Johns Hopkins University. And in this particular case, we're looking at, we install a burglar alarm. And the burglar alarm goes off if there's a burglar, but it also goes off if there's an earthquake. And you know that you have neighbors who might call you if the alarm goes off. And you know the probability that John will call you and the probability that Mary will call you, given that your alarm goes off. You also know a few other probabilities. My cat is very happy, as you can tell. Here's what it looks like. What this diagram says is burglary and earthquake have an effect on alarm. They cause alarm. Alarm has an effect on whether John calls or whether Mary calls. This particular kind of graph is called for the DAG, Directed Acyclic Graph. What it means is the directed means that the connections only go one way. We don't have a connection from alarm to earthquake. We have a connection from earthquake to alarm. Most of the graphs we've looked at have been bidirectional. If we have a connection one way, we've had it the other. But the directed graphs are not. Then it says it's acyclic. What that means is you can't start at one place and go down and get back to that place. There are no cycles in the graph, which means you can't go around in circles literally, which is very good. Now, this is how a Bayesian network is set up. You have the probabilities you know. You know that there's a probability that there'll be a burglary is 0.001. And an earthquake is 0.002. It looks like you must be living in an earthquake zone or something. If there's a burglary and there's an earthquake, it's 0.95 likely that your alarm will go off. True and false, these numbers are gotten from experience. Further, you know something about John and Mary. If the alarm goes off, John calls. If the alarm doesn't go off, he might even call. Mary's in the same boat. Now, the question is, did you got a call from Mary? Pardon me, I think from John. Is there a burglar? And the global semantics basically says the probability of a joint distribution, that is, the probability that all the things are correct, equals the product of the probability of each of the events, given that you have the parents. So in this case, J means John calls, M means, let's see, I got to make sure I understand what's going on. The neighbor John calls, but the neighbor Mary doesn't call. So I thought that would be a not M there. And that there's not a burglar and there's not an earthquake. This isn't the same one as above. This is slightly different. In other words, if the two of them call you, there's about a 0.00063 chance that there's neither a burglary or a earthquake. And you can compute this for other possibilities too. Now, that's roughly how this is done. I also have something else I want to show you from the web. See if I have the right one. No. I have to go here. I think this is what I want. No, pardon me. It's here. It's the 10. Here we are. Here are some of the applications of Bayesian networks. Gene regulatory, medicine, biomonitoring, document classification. That means things like determining if the email is a scam. Information retrieval, semantic searches, image processing. As you can see, there's a lot of real-world applications of this particular technique. And there's lots of places on the web, but most of them are a little hard to understand, to be honest with you. They go into a lot of probability, and you have to sit down and think about them. I've been looking through some of them. That's what I want to say at this point. I will put out this particular document in a few minutes. I hope that you are having a good time. I apologize for using a disease in this. I know it's kind of sensitive, but unfortunately it was the only example I could find that was well worked out and easy to understand. So please forgive me. I'm not trying to hurt anything, but I had little choice. Thank you now. Bye.